Okay, what happened? You were quiet and then all of a sudden. Hello? Everybody? We're going to start any minute. Okay. So, you finished earlier than last time. Does that mean it was a easy quiz? What? No. No, seriously, was it, did you struggle with anything? What does that mean?
It wasn't super hard, but bad either.
So it's like in the middle, it wasn't like a thumbs up, it was a thumbs. Yeah, go ahead. Ask. If you slowed it too much, it will actually cause some widening of the peak. Because then you don't have enough speed in the flow rate, you'll have more longitudinal diffusion. We want less longitudinal diffusion, but it shouldn't be too fast either, because if it's too fast, you don't give it enough time to interact with the column, and it comes out too fast, and you have coelution. So too fast will get coelution. Too slow, you have broadening and coelution, and you want an optimum flow rate. So the answer is true. What was the question?
If you slow it down and then you have a
Yes, the longitude and thus resolution of two peaks may worsen. So it's true. Yeah. So it's the key is TFTTF, I think. Yeah. Yeah, you can't use gradient illusion with IR, right? Not IR, refractive index, RI. Yeah. We talked about it last lecture. Okay, so, and then the other question was based on lab mostly, so hopefully you remembered stuff from lab. Okay, why are you talkative today? A lot of energy in the room. What? What?
We're relieved.
You're relieved? Yeah. So you're happy?
No. We just get to check something off our list. I'm relieved. Check it off my list.
Okay, so calm down. Now I'm going to start a very boring topic. Will put you to sleep. But no, seriously, it's a very important topic.
I think it seems important.
Whether it's boring or not is beside the point, but it's a very important topic. Guys, ladies. Okay, so it's important because a lot of analyses that we do in food analysis is, okay, how about I give you 5 minutes to chat? Let everything out of your chest and then I can start the lecture? What? Okay, I'll let you out 5 minutes early. Just give me your attention now. Do you know that song, All She Wants Is Attention? Oh, yeah. Okay, so give me your attention. Okay, a lot of analyses in food analysis relies on spectroscopy. So it is a very important topic. Now, whether it is easy to comprehend or not, it's another topic. But really, you want to remember your optics physics a little bit, so we're going to review that. Yeah, I know. We're going to review this a little bit to understand the principle of spectroscopy and how it works. And then once we understand the spectroscopy and how it works, we'll have chapters of applications. So today and probably Friday, we'll do general introductions, and then we'll do different specific spectroscopies. All right. Let's remember optical physics. Makia. C? Just C. Okay. Any other? Riley? It is all of the above. So you can explain light in terms of a wave, and a wave of light is composed of electric and magnetic field. And then you can explain wave or light in photons of light, pockets of energy. And understanding absorption of light and emission of light is mostly through understanding it for using the photon principle. Okay, following spectroscopy as means of analysis, detection can be based on Peter? All of the above. And everybody agrees, or do we have another Mallory? It is just A and B. Dissipation of heat, it does happen. So, you know, when a molecule or an atom absorbs light, it goes from a ground state to an excited state. And then when it won't stay at excited state, it's just going to go to the boring state, which is the ground state. But while doing that, it can either emit back the energy in a form of photon and photon. Oh, not photon. Okay, so it either emits it, and that's when you measure fluorescence, or and also fluorescence, it does include dissipation of heat. So it gives energy in a form of heat, and it gives energy in a form of photon. So it does, but dissipation of heat is so small, so the heat is very, very small, you cannot detect it, or you don't have a way or an instrument to detect this amount of heat, small amount of heat is released. So we cannot rely on dissipation of heat for quantification using spectroscopy. So either we're measuring absorption of light or we're measuring emission of light. So I'm trying to sum up spectroscopy. What is it? It's an interaction, a study of interaction of radiation with matter, basically. And the matter, you have different species. So you have either a molecular species or atomic. Some of you did AA, atomic absorption. So we were working with atoms. We're breaking the molecules into element form, atomic element form, and measuring absorption of the atoms. Or you just measure the absorption of molecules in the molecular form. So, and then the interaction with matter, the radiation interaction with matter, can be in the form of absorption, and you measure absorption, in the form of emission, and we measure fluorescence, or it could be light scattering, like the light scattering detector we talked about last time, where it's a universal detector and the particulates scatter the light, and the amount of light scattered is correlated to the concentration. Or diffraction, which is a very important principle for generating wavelength of similar length and having an absorption at a particular wavelength. And we'll talk more about that. Diffracting the light into individual wavelengths, light with one wavelength. Okay, the other important phenomena is the region. Where are we measuring absorption and where are we measuring emission? So, as you know, radiation of light ranges from radio radiation to gamma rays. So radio are the largest, so they're like 100 meters long. A very large, the wavelength is really long. And the gamma radiation is a very, very small, 10 to the negative 10 meters. The region that we care for in food analysis is UV, the ultraviolet, the visible range, and the infrared range. That's where we do all of our measurements, or most of them. Okay? This will talk about the energy. The longer the wavelength, or the smaller or shorter wavelength, it carries more energy. Okay? Shorter wavelength carry higher energy. So that's what the arrow designates. And we'll talk about that when we explain what makes a wavelength carry more energy. Okay, so these are the different types of spectroscopy that is relevant to us in food analysis. So absorption, a lot of different methods are based on absorption. Fluorescence, few are based on fluorescence, especially those compounds that fluoresce and are present in small concentrations, like vitamin. Infrared is a very important region for measuring absorption of light because it helps with structural elucidation. Atomic absorption and inductively coupled plasma emission, we'll talk about that in the chapter of atomic absorption and emission. So we did, half of you already did the atomic absorption in lab to measure minerals. Nuclear magnetic resonance, there's a chapter in your textbook. If you're interested, you're welcome to read it. Otherwise, we're not covering it in this class due to time. And this is my excuse, due to time. I don't like NMR. But it's due to time. We don't have time to cover that chapter. So mass spectrometry is not spectroscopy. It's not interaction with light. A lot of people sometimes have this misuse of the word. They say mass spectroscopy. Don't do that. Gary will yell at you. So it has nothing to do with light interactions. It's a different type of spectra. They have the spect in it because you generate spectra. Spectra, either an ion spectra, mass ion spectra, or M by Z spectra, or a light-related spectra, absorption or fluorescence or IR, UV, vis, or IR. Okay, just wanted to make that clear distinction that mass spectrometry is metry, not scopy. Okay, applications. Why and where do we use spectroscopy? Can you think of anything? Any applications from what I've talked so far? Sarah? Measuring color. Yeah, you can measure color by spectroscopy in the visible light. Okay, but in food analysis, if we want to use the color to analyze, okay, so we do quantification of different components by either the compounds are naturally absorbent of color, they absorb light, or they are, we react them with the reagent and produce a compound that absorbs light. And this is how we do quantification. So quantification of different components of food. What else? So we do quantification. What else we do? We can use spectroscopy for. What? Gas? Gas or guess? IR?
Gas, air.
Air? What do we want to do with air?
Not air, but gas. To shine,
Application. How is, what do we, I don't get, I'm not sure I got you. My question is, what do we use spectroscopy for? So quantification is one. Identification. So identification of a presence of something. Maybe we don't want to quantify. We just want to know, is it there or not? So we can do, we call it qualitative analysis. So for qualitative analysis, for quantitative measurement, I did say something earlier in the other slide. What does IR do for us? Infrared. Structure elucidation. So it can give you information, it can give you information about structure. So structure elucidation. So, and let's see what else we have. Compositional analysis was part of a it is under quantification, but it's specific for composition, like what you did, or some of you did in the lab, did calcium and iron, that's composition. Compositional analysis. Sugar, for example, you can do an enzyme assay. Of course, glucose or sugars don't absorb light, so you react them, produce a compound, and then measure the absorption of light. Quality assurance and forensics. We'll give a lot of examples about forensics, looking for unknowns and something wrong with the sample. For example, milk. I want to know if the milk is contaminated with melamine. I can run an IR and look at, is this an IR spectra that is normal for milk, or do I see a unique structural peak or spectra related to melamine? So a lot of different applications, and especially in food analysis, and we'll be covering a lot of examples. Here's the best part, physics of light. So light or electromagnetic radiation, you can explain light by the phenomena of wave-like property, or you can explain light by photon properties. So if we want to think about it from its characteristic of being a wave, so you have the electric field oscillating with magnetic field. So defining a wavelength, you heard me say wavelength multiple times. When we did the caffeine lab, I kept saying lambda and lambda max. So let's review that. What is the wavelength? The wavelength, I keep forgetting this. The wavelength is the length from two maxima, between two maxima of one oscillation. So that would be a wavelength, from maximum to the maximum of another oscillation. What's the frequency is how many oscillations per unit time. So how many 1, 2, 3 per second you get. The more oscillations you have per unit time, the higher the energy. That's why shorter wavelengths will give you higher energy, because you will have more oscillations. So let's look at it like that. So if I have, this is a short wavelength versus longer wavelength. So in 1 unit time, let's say 1 second, we have several. So this carries more energy than this in 1 second. So that's why shorter wavelengths associated with higher energy. Amplitude is the magnitude of the electric vector. So it goes, the amplitude is from the axis to the maximum point of the electric point or electric maxima, electric field maxima. So the wavelength or the wave-like properties help us understand 3 important phenomena: interference, diffraction, and refraction of light. Interference of light is important for us, and it's used in IR spectroscopy. And we'll go back to that when we cover IR spectroscopy. But what is interference of light? So you have 2 different waves that might interfere with each other in space. So if they interfere where maxima and minima overlap, that's amplification. So you increase the power of this wave. So you have higher amplitude. If they interfere where the maxima overlaps with the minima of another wave, they cancel each other. Okay. So in IR instruments, they position the light and put mirrors in there to get certain amplification and sometimes reduction, depending on the output and or what we want to achieve, and then I'll cover that in the IR chapter. Diffraction is very important when we want to measure light at a specific, or absorption at a specific wavelength. So we want to diffract the incident beam, the light source. It has it's made up of multiple waves of multiple wavelengths. So we hit diffracting or grating system, diffraction grating system, where it breaks kind of the light, we call it diffracts the light, into individual waves with singular wavelength. So each wave would have a one wavelength. Refraction of light is important, for example, in refractive index. So it is the incident beam when it hits a surface of another medium and goes through that medium, it refracts. You have a refraction angle. And it's important for measuring total solids, for example, or total soluble solids, because when you have more solutes in there, you will have larger refraction angle, changing the direction of the light. So, but like I said, absorption and emission of light is better understood if we think about the particulate properties of the light as photon. So a wave is discrete pockets of energy. Just think about it, pockets of energy. Each pocket of energy is called a photon. The energy of the photon can be defined in terms of frequency. Okay? So energy, H is a constant. This is the V is for frequency. Again, frequency is how many oscillations per unit time. The shorter the wavelength, the higher the frequency, the higher the energy. Okay. So again, you heard me say in the HPLC lab, monochromator or monochromatic light. What is a monochromatic light? Mono? One wavelength. Light consisting of, or waves of light that have the same wavelength. So electromagnetic radiation composed of waves having a single frequency and wavelength. Okay. So, and then there is this unit that we call monochromators, which is the unit or a system that generates monochromatic light. So a monochromator is a unit that usually you have mirrors because you want to contain everything in a small spectrophotometer. So you would put mirrors to project the light. So here's your incident beam. So the incident beam hits a mirror in the detector and then reflects onto a grating system. The grating system breaks the light into wavelengths of singular, or waves into of singular wavelength. And then there's a filter, and you adjust the filter, this can move, to select waves of one wavelength. And then it would go, hit a mirror, again because everything is contained in a small unit, and then this beam can go, and then let's say there is a cuvette here with your sample in it, and that sample will absorb a monochromatic beam or light. Photon flux. A photon flux is number of photons flowing across a unit area. How many photons are hitting a unit area at a particular time, basically. And then lastly, brightness or radiant intensity is the energy that hits a certain area per unit time. This is important because sometimes you change the brightness of the lamp to make sure you have higher sensitivity to detect at low concentrations. This is very helpful to regulate the brightness. Okay, I said I'll let you out 5 minutes early. Okay.